MDM4U 3.2 Linear Regressions. Regression is an analytic technique for determining the relationship between a dependent and an independent variable. So a regression model describes the general trend that we see by the points in a scatter plot, which is a graphical display for two variable data. Linear regression is an analytic technique for finding the equation with the form y is equal to ax plus b that best models the relationship between two variables. So notice that this is just like the form y is equal to mx plus b. It's a degree 1 polynomial, meaning the exponent on x is 1, a representing the slope, and b representing the y-intercept. So that being said, this line of best fit is representing the general trend, and we would say that the equation for the line of best fit is the y estimate. So when we substitute in the value of x, this is approximately where the value will be for a given value of x, as predicted by the line of best fit. However, whenever we substitute in different values of x, in this set, the minimum point is 2 and the maximum point is 8. So when we make a prediction using the line of best fit from within the data, this is referred to as interpolation. So this interpolation is an estimate using the regression model between two known values. So that's the x minimum and x maximum in red on the diagram. Extrapolation is an estimation using a regression model that is beyond the range of data. So if this is the range of our data, if we were to continue to use this line of best fit as an approximation of our trend, then this is extrapolation, and oftentimes what we're doing is trying to make predictions using our model. Note that the values or predictions within our observations, or our x min and x max, is likely to be closer to the truth of what we would observe if further data was compiled. Note, outliers in a set of data are significantly far from the majority of data and can reduce the accuracy of a model in small samples. So it will adjust the line of best fit to accommodate the discrepancy, as well as smaller samples means that it has a more significant impact. So sometimes they're even removed entirely from the set of data to represent most points. Okay, so we at this point have drawn lines of best fit by hand, but to truly have the line of best fit, we need to apply the least squares method. So first we need to define the residual. A residual is the vertical deviation of each point from the line of best fit. So this is your y estimate from the line of best fit, and these are the data points. The vertical displacement is this side here. And what we can do is, if we were to look at the vertical deviations, that is y minus y estimate. Y minus y estimate in this case would produce a positive value because y is above the line of best fit. And in this case, y minus y estimate would produce a negative value. So if we were to add these areas, the positives and the negatives will be canceling each other out. For the line of best fit in the least squares method, the sum of the residuals is equal to 0. The positive and negatives cancel out. The sum of the squares of the residuals has the least possible value. That being said, this formula, y is equal to ax plus b, can be accomplished, the line of best fit, by determining the value of a by doing this calculation here. And we'll look at how to calculate this by hand using a table of values, because this would be challenging to write in one line by hand. And b, the y-intercept, is given by y minus a x bar. So the y bar and x bar just representing the average for both of those variables. Let's take a look at this in context. Apply the least squares formula to determine the line of best fit. So if this is our data, I'll highlight this and I'll copy this for future use. Let's say that this is the age of an individual and their income in the thousands of dollars. We can sometimes reduce the number so to make calculation easier. That being said, in order to be able to apply this formula, remember we want our end goal to be something in the form y is equal to ax plus b. So we have to determine a, which is given by this formula. So that means that we need to have n, which is the number of points. Remember that in a scatter plot, that these pairs each represent 1 point. So there's 1, 2, 3, 4, 5, 6, 7, 8. The sum of x, y. So that means that for every single pair, x times y, we need that value. And by taking the product of x and y and adding them together here at the bottom of the table to get the sum of x times y, adding all these values, we can have that to substitute. Minus the sum of x times the sum of y. So here's x, here's y, the sum is written below, and it can be substituted into the equation. Next, we discussed that n was 8, but the sum of x squared and the sum of x then squared, we should just take a close look at the following. The sum of x squared means that we need each term with x squared. So 33 squared is this number, 25 squared is this number, and then add those together to get the sum of x squared. Notice that that is different than the following. The sum of x in brackets squared, the squared is affecting what is the base, which is the sum of x, so that's 292 squared. So we determine our value approximately for A, and then to determine B, we will need y bar and x bar. So all that we need to do is we already have these sums, so we divide by the number of elements in the set, which is 8 for each, to get those values. And we determined A from our previous calculation, therefore we can calculate B. And this is our line of best fit. So one way to check, we can highlight, Control C. Let's take a look at Microsoft Excel. So I'm going to Control V, paste the information into this table. And what we can do is click and drag over top of the area that we wish to plot, insert, and we'll select the scatter plot. Now this right here is going to be with the title Y versus X. And I'm going to move this over because we also want to include some details about this. I'm going to zoom in. Give me a minute. So, that being said, maybe we'll go here. Okay, just want to make sure this is in the viewing window. So we click on the data points, and when we right click, we can add a trend line. So this will automatically add the line of best fit, and we can extend that by typing in values for forward and backward. But let's look at the following. Down here, we can display equation on chart. And to go one step further, we can also display something called the coefficient of determination, R squared. This is going to be our value for the correlation coefficient learned in the section 3.1, but we need to take the square root of this. R squared applies to both linear and non-linear models. Okay, so we can check our answer. 1.15 is what we approximated as, minus this value. Let's just see if that corresponds. Success. Okay, so try these questions. Let me know if you have any questions.